you have any parameterization of the curve. So let's make a picture of it. So imagine I have an interval J, okay, and I have another interval I. So that's an interval J, and that's an interval I. Then, and maybe I have, okay, so I have interval J and I have interval I, and phi is a map that takes me from J to I. Okay? And I is the domain of the P. So the P is going to take me I to where? So it's going to take me to the path actually. So it's going to throw me onto the path. Are you getting the point? So this is what, this is P of phi of t. Okay? And what we are saying, can you see J mapped onto I and the I mapped onto this path actually, so you can call it as P of phi of t. And we are saying that this P of phi of t should be same as Q of t actually. In other words, you can get this curve directly by mapping J in a space R going through this path. You're going to eventually meet or reach what you call the same curve. Okay? So if this is the case, you're going to say that Q is the reparametrization of the P. Okay? And both are parameterizing the same curve C actually. Okay? They both are parameterizing the curve C. And this phi, or the phi, okay? Phi P, okay? This plays a crucial role of taking you from the interval J to the interval I actually. Okay?
Yes, sir.
I know it's boring, but let's do one example of it.
Sir, so when we reparameterize and we change from domain I to J, then sir, what relation there will be between I and J? Because here it seems that J, I is a subset of J because
there are,
sir,
there can be two very different intervals of the real numbers actually. So both are intervals, they can be very two different intervals of the real numbers. Are you getting the point? So let me give you an example. Let's do an example. Let's think about what interesting things that this can do. And the example is going to be about the unit circle. So the first is unit circle. So unit circle is what? It's a collection of a point. So it's a curve in R2, I know that. XY is a collection of a point in R2 such that x squared plus y squared is 1 actually. Okay? And how it is usually parameterized. So you usually parameterize this curve as a map from 0 to 2 pi into R2. Okay, and you define it by P of t equal to this cos t and sin t. Okay, where the t is a map from t to pi. Okay. This circle, and I'm saying, so anything that satisfies this constraint is a parameterization actually. So this can also be parameterized by, say, Q of t equal to, so that's one parameterization of it, Q of t equal to say sin t and minus cos t. Would that satisfy the equation? The answer, it would still satisfy the equation. And take the t from interval say pi by 2 to 5 pi by 2. Pi by 2 to 5 pi by 2. So is this a parameterization of the circle? Yeah, it's a parameterization of a circle actually. Because if you plot all these points, you're going to get the same picture as this circle. Okay? And the good thing about what these two parameterization is what? They both have different expressions. and they both have different domains, but they are still parameterization. The question, can I go from this parameterization to this parameterization? Okay. The answer is, not. Okay. But if they both satisfy such a condition and such a phi exists actually, so what you need only, the only thing that you need is this map phi actually. Okay. So what do you think, what should be the phi? So phi should be a map, okay? Phi should be a map from which interval to which interval? Pi by 2 to 5 pi by 2 into 0 to 2 pi. Okay? And phi of t should be what? In many cases? Many cases. So here's the thing. I need to substitute the phi into the p. And p is what? Cos t sin t. So what changes should I make? Obviously I can only change t. In t in such a way that cos becomes sine actually. And sine becomes minus cos.
So odd multiple remaining multiple of cos and sin.
क्या मतलब?
So cos और sin एक दूसरे के odd multiple है.
Odd multiple.
Angle का कोई.
Okay, so what is the relationship actually?
T minus pi.
T minus?
Pi.
T minus pi or T minus pi by 2. T minus pi by 2 would be the case. So define T to be T minus pi by 2. So you can guess it actually. It's not a big deal. Can you see what will happen? So in other words, take your P of T, which is, now is this map well defined? That's an interesting question that we must ask. So if you choose T from pi by 2 to 5 pi by 2, is this output is between 0 to 2 pi? So it should be. It should be. So in other words, if you, for example, subtract, pi by 2 from the both part, so you're going to get a 0 here and you're going to get a 2 pi here. So everything is fine. Okay. Make sure that definition follows it. Okay. So the phi of t is t minus pi by 2. And now take this phi of t and substitute it into the p on the place of the t. So what are you going to get? Cos phi of t, sin phi of t. Cos t minus pi by 2, sin t minus pi by 2. So the cos t minus pi by 2 would become and sin t pi by 2 minus pi. So you have a parameterization and you have a reparametrization of the curvature. And you define that reparametrization by taking a map out. Okay? So here we guessed the map. But we can also do, okay, here's an important thing. Think about it. Does this phi satisfy all these definitions? So is it continuous? Is it smooth? Obviously smooth, it's differentiable and everything. Is it regular? This phi. You differentiate it, what are you going to get? You're going to get 1 always actually, no matter what t you have. Okay, so it's regular as well. Is it monotone? Yes, it's a linear function. So I know that linear function either goes up, r goes down, r stays same actually. So there is no other way around. So it satisfies all these properties actually. Okay. So whenever you are thinking about this, okay, you also just quickly think that whether the assumptions are true or not. So everything is true. Instead of this, okay, so here I fixed 2, so parameterization and reparameterization, and I found phi. I can do another thing. So just take any function, any phi of t, okay, of your choice. Okay, make sure it must be well defined. In other words, it can take values from whatever choice of your interval is and throws the values in 0 to pi by 2 and satisfy these properties and substitute it into the P of t. So you're going to get different parameterizations of the circle. So that's just one possible. You can have lots of other different parameterizations of the circle as well. Okay? I'm getting the point. So I'm going to say this Q of t is a reparametrization of the curve. It's a reparametrization. One more example. Consider this xy x square plus y cube equal to 0. Okay, so I have a curve that is defined by this rectangular equation. Okay, and when you're gonna plot it, you're gonna see that you're gonna get semi-cubical parabola. Semi-cubical parabola. Okay, this will be distinct like this actually. Yes, we have x and y axis is going to be just opposite of the cusp that you saw previously. Okay. All right. So that's your C. So can you guess one parameterization for this curve? So what would be the obvious way to parameterize the guess parameterization of the curve?
Minus x.
So take x of t to be say t. Then y of t must be
3 by 2. Y power 3 by 2. T power 1
Let's express the y in the terms of it actually. So
minus
t raised to
T power minus 2 by
3 by 2.
T power minus 2 by minus t
minus t
whole power minus 2 by
3 by 2.
3 by 2, 2 by 3.
3 by 2.
2 by 3. Some people are saying 2 by 3. Make sure who is wrong or who is correct.
Yes.
Okay. So I have one parameter, P of t equal to t and minus e raised to by 3. Okay. So you have it. What would be the derivative of it? T prime of t is going to be 1 minus 2/3 and t raised to minus 1 by 2 1 by 3, okay, and evaluate it at t equal to 0. So what is that? This curve is not regular. It's not regular. Why it's not regular? Because this minus is a trouble actually.
Denominator.
It's minus is a trouble. It's going to go in the denominator and mess up the things actually. Okay? Let's think about another parameterization of it actually.
सर लेकिन इसमें एक तो सर 1 है
ना. Okay, so yes, you're right. You're right. So it's gonna be, but okay, still is a trouble that it doesn't exist.
दूसरा component.
This doesn't exist actually. It's 1. So the first requirement is that p prime of t should exist and it shouldn't be 0. So there are two things actually. So it fails the first condition that it doesn't exist. Okay? It doesn't exist. Origin is the problem. Can you guess another parameterization of it? So what would be another parameterization of this curve actually? So I have x square and y cube. So I need to add two quantities and I want to turn them 0. So just take both of them as
1 and minus 1.
1 and
Minus 1 is y is equal to minus 1 and x be 1.
how about this one? Okay. So take okay. So if I substitute t in both, I'm going to get what? T square plus t cube equal to 0. Minus t करें तो what are you going to get? But still you're going to get t square and minus t cube. So you need to balance the powers as well. So what should I do? How about? Yes, that's a good trick actually. That use this to x to be t cube and y to be minus t square actually. Get it? We have another parametrization of this curve actually. Okay. So what's the good thing about this parametrization? The good thing about this parametrization is that at least the derivative exists actually at the origin. So here this p was not even so the p was not even smooth actually. Okay, so this is not a smooth parametrization because this derivative doesn't exist. But okay, this still has a problem. If you compute k prime of t and you get 3t square and 2t square and at origin it becomes 0, but it has an additional part that it's smooth actually. Okay, so it's continuous and it's differentiable as well. So singularity is still there because it's inherent to the curve. Okay, you can't just take away the singularity unless you take away this kink out of your curve. But the good thing is that you reparameterize and your smoothness issues is resolved actually. Okay? So it would be a good point to think that what shall I choose? So what should be the phi of t here that can take you from the one parametrization to the other parametrization? Any guesses? So I want to go from here to here. So what should I do? And it's very easy. Think about it. So what should be my phi of t? So it must be. So I want a cube here. So I need to replace t by cube. But if I replace t by cube, what will happen to this guy? Minus t square. So wouldn't that be the same thing actually? So the phi of t should be this must be the parametrization. In circles example. Okay. You have to think cleverly, maybe it would not be that trivial to find it, but yes. Think about it.
Sir, in this example we're working on circle. How circle is monotonic, sir?
How circle is?
Monotonic.
Is circle monotone?
So we are phi.
The question is it a function in the first place actually? Not a function. Forget about the monotonicity of it actually. So, yes. So if you just take on one part of it, still it is not monotone. So it increases and then decreases actually. There's no point of monotonicity of it. Okay. Alright, so 15 मिनट लेट आए हो 15 मिनट चाहिए ठीक है because we have done nothing except few definitions actually तो खास इतनी चीज की नहीं अगर समझ आ गया तो it's just a 10-minute thing the other thing is but it's good that you absorbed the definition. So let's get So the next thing that I would like to define, or maybe make you think of, is the orientation of the curvature. Okay? Orientation of a curve, or orientation of an object. Okay? Orientation of a curve. Curves are important to study curves, because one way it is that we can think of surfaces as something made up of the curves. Another thing is that, okay, if you are not ready to think something that surface is something that is made up of the curve, look at the boundaries of the surface actually. It always will be curved. Okay? The next thing that I would like to talk about, keeping in view this notion in your head, I would like to talk about is orientation of a curvature.